Okay. Thanks for the introduction, and thanks to the organisers for this invitation and this opportunity to speak here, and for inviting me to be part of this programme. It's been great fun. I also have the particular privilege that I also gave a talk at the opening workshop, and so I have the slight challenge that I want to give a talk that doesn't seem boring and repetitive to people who were at the opening workshop, but also isn't completely incomprehensible to people who weren't. So I'm going to try and do that, and you can judge for yourself whether I succeed or not. But I mean, there are lots of things I could talk about, but when I have an opportunity to talk to this audience, the thing I really want to talk about is the problem of how to do parameter inference for stochastic reaction networks, because that just seems like it's an important problem, and I think there are lots of interesting algorithms one can use. And the whole issue of parameter inference has cropped up several times during this workshop. It's been mentioned several times. We've had mention of moment matching, we've had mention of Bayesian methods, MCMC, ABC, SMC. But what I want to try and do is dig into what these things are and what their pros and cons are and how they work, and try and demystify them a little bit. The other thing is that I don't think anybody mentioned particle MCMC algorithms, and actually they're my favorite approach to this problem. But I talked about those at the opening workshop, so I'm only going to mention them very briefly in this talk. But I would encourage anyone who is interested to maybe go back and watch the video, which I guess is online, if you think particle MCMC methods look interesting after this talk. Okay, so here's a quick overview. I'm going to talk very briefly. I'm not going to repeat all of the usual stuff about stochastic reaction networks, but I'll just set the scene, give an example model, talk about the issue of stochastic simulation. I will explain what I mean by a partially observed Markov process or pump model, and I'll talk about some of the different likelihood-free methods for inference. Okay, so I'll explain what I mean by likelihood-free and why that's interesting, but also what the issues are. And I'll talk about some of these algorithms. So the particle MCMC algorithms I'll mention very briefly and illustrate how they work, and then I'll talk about some of these other algorithms and compare and contrast them and try and give some pros and cons of the different approaches and how you can actually put these different algorithms together in a constructive way. Okay, so the running example I'm going to use for this talk is my second favorite kind of example stochastic reaction network. So at the opening workshop I used my absolute favorite, which is the Lotka-Volterra predator-prey reaction network. This one mathematically, of course, is quite similar. It's just another stochastic reaction network. From a mathematical perspective, there's not such a big difference. But from a computational perspective, this one is like orders of magnitude more complex for reasons that I'll explain. But just to set things up, the idea is that we have a gene. It leads to some RNA transcripts normally when it's turned on. That in turn is translated into a protein. The protein forms dimers, and the kind of catch is that the dimers can actually bind to a regulatory region upstream of the gene, which prevent transcription. Okay, and so what you find is that this system auto-regulates itself. When the gene is turned on, you get more protein, but when you get more protein, it's more likely to turn itself off, and so the system auto-regulates. Okay, so that's quite a simple model, but it means there's lots of things going on, and there are things going on at different scales, different space scales, and different time scales. So it's kind of an interesting system, and this kind of system is used, in biology by, it occurs a lot in bacterial networks, this kind of autoregulatory system. Okay, so we could turn that into a set of reactions. Okay, so here there are going to be 8 reactions if you count the forwards and backwards for these two reversible reactions. So there's the gene being turned on and off, there's transcription, there's translation, there's dimerization, and there are 2 degradation reactions. So we've got 5 species and 8 reactions. I really like these graphical representations of stochastic reaction networks. So here it is as a Petri net. Okay, so here the species are represented by the circles, and the reactions are represented by these rectangles, and so we get this nice kind of bipartite digraph representation. And the nice thing is it does reveal structure in the network. So here we see this loop in the in the autoregulatory network, and that corresponds precisely to that feedback loop. And the interesting thing is that you're going to have very high copy number species talking to very low copy number species, and that's one of the challenges of this model. Okay, so we all know how stochastic reaction networks work. You go somehow to a stoichiometry matrix, and then you kind of define your mass action hazards. You simulate it with the Gillespie algorithm or whatever. I don't need to repeat that. So somehow you can simulate traces. Okay, so here's an example trace where I concentrate on 3 species. Okay, so here we look at the RNA transcript levels, and you see these are very low copy number, 1 or 2 molecules, or most of the time 0 molecules. We've got the protein and we've got the dimers here. Okay, so what you see is that despite the fact that the dimers are very high copy number, you know, we've got 400 molecules here, it's still got very, very bursty, discrete stochastic behavior, and that's because it's really quite tightly coupled to these very low copy number species. So that's challenging. The other challenging thing is that I haven't even bothered to show you the gene, the state of the gene, whether it's bound or unbound, because that's just happening on a much, much faster time scale than this. So it doesn't even make sense to look at that, right? The gene is being bound and unbound so fast that you can't even see anything sensible on this kind of time scale. Okay, so this is a good example of a nice multi-scale model, quite challenging to simulate. So although it's not like a huge model with dozens of reactions and, you know, lots of species, right? It's quite challenging for both simulation and inference. Okay, so I've said a lot of this stuff, and I guess if you're into hybrid algorithms, then this would be a good example for a hybrid algorithm. You've got this separation of scales. But it's challenging even for some of the hybrid algorithms we've heard talked about this week, because it's not enough just to partition into kind of fast and slow reactions here, because you've got those low copy number species that are very fast. So you'd actually need a really quite sophisticated hybrid algorithm that included some kind of averaging for those low copy number species as well. So it's quite a challenging model. So I'm just going to duck that completely and use the SSA to simulate it. That means that everything runs really slowly, which is very frustrating, but you know, given that I don't really have a hybrid algorithm to hand that I can trust to simulate this correctly, I'm just going to use the SSA and take the computational hit. Okay, so another thing that's sort of come up a few times in this workshop is this whole issue of modularity, of decoupling models from the simulation algorithms. Okay, so if you're doing modeling, it's no good having a simulation algorithm that kind of has the model hard-coded in it. So you can't just try another model without kind of doing a bit of maths and doing a bit of programming and rejigging your simulation algorithm, right? Okay, if you're doing methods development, that maybe is okay, but if you're doing modeling, that's really not okay. You need to be able to just have a model, shove it into your simulation algorithm, get simulation results out. You have to have that decoupling, otherwise you can't do model exploration. So this is a very important problem, you know, generally, for all simulation algorithms, but I think it's also important for inference, and so I'm going to come back to that in the context of inference. Okay, so there are obvious benefits to doing this, right? It's much easier to modify a model representation than it is to modify a simulation algorithm. When you're trying to build big models, it's much easier to visualize and analyze. It means you can use different simulation algorithms with the same model, which is also very important. So, you know, you can try the SSA if it's too slow, you can try a hybrid method. If you've got a hybrid method you don't trust, you can cross-check it against the SSA, etc. So there are all kinds of obvious reasons why this decoupling of a model from a simulation algorithm is important, and that remains important in the parameter inference context as well. Okay, so what is parameter inference? Well, of course, we all really know what parameter inference is, but if we take this simple example here, this autoregulatory network, it's got 5 species and 8 reactions. So what might the parameter inferences be? Well, each one of those reactions has a rate constant associated with it. So there are 8 things that are potentially unknown, so we might want to estimate those from data. Of course, to simulate it, you need an initial state as well, and sometimes you might not know the initial state. So the initial state of each species could be unknown parameters as well. Even in fact, the structure of the reaction network itself could be uncertain and could be embedded into the parameter inference problem. Now, people don't normally consider network inference to be parameter inference. They consider that to be a separate problem, but in fact, you can embed it into a parameter inference problem, right? So for example, if you have a reaction that you're not sure it's there or not, well, maybe that rate constant is 0 or not, right? So just by having a binary indicator for whether or not a reaction is present, well, that binary indicator is then a parameter, an unknown parameter that you can do inference for. So it's actually quite useful and constructive to embed the model selection problem into the parameter inference problem. And the algorithms I'm going to talk about today can be used with discrete parameters determining network structure without much trouble at all. Okay, I'm not going to explore that today, but they can be used for that problem. Okay, and so then you're going to need some data to do this, and again, that varies from field to field, but here in the context of these stochastic reaction networks, it makes sense to think about having time course data. And so in the biological context, ideally we're thinking about things like time-lapse fluorescence microscopy data on some of the species in the model. Okay, but your data is going to be lousy compared to what you would really need to identify all of these parameters accurately, okay? And that's, again, a really important thing to understand, that, you know, parameter inference isn't magic, right? You can't have a model with like 30 parameters in it, some really terrible time course data on one species, and run some optimization algorithm, get some numbers out and say, these are the parameters of my model, right? That's just not how it works, right? Most of those parameters, there'll be essentially no information about in that data. So you can run an optimization and you can get an optimum, but it's not telling you anything really about what the real rate constants are, what your real uncertainty is about those rate constants. So you need a method that takes that into account. Okay, so again, for my running example, we're going to have this autoregulatory network. Here I've simulated it over 500 time units, just recording its state every 10 time units. So I know the true state of the system at each of those 50 time points. But all I'm using for my data are noised up observations of P and P2. Okay? So I'm only measuring 2 of the species, and I'm measuring those subject to error. Okay? And you can see that the error is quite significant. So with this one, okay, you can probably figure out roughly what this trace looks like from that noisy data. But if you look down here, right, the noise is really very significant compared to the level. Okay, so again, this is a realistic, challenging scenario. Okay, so it's really hard to say much about this trace. Certainly, it's very hard to say much about the noise in the dynamics of this trace from that very noisy data. Okay, this one you at least have a chance of spotting these big jumps. Okay, so there's some information in here about the parameters, but there's clearly not going to be enough to really pin down all of the parameters of the model. But that's just life. That's the way it is. Okay, so.
What are the 2 parameters?
What are the what?
The 2 parameters that you're measuring?
So it was the protein monomers and the protein dimers. Now, of course, there's a challenge there in doing. I don't know how you'd construct fluorescent reporter system, but that's not the point, right? It's just 2 proteins. Yeah.
And your data is that synthetic data?
Yeah, of course. Yeah. So we can see how well we do. Yeah. Okay, so the Bayesian inference problem then is how can we say what we kind of know about the rate constants on the basis of the data that we've observed. Okay. Now, of course, people have been tuning models to data for centuries, right? So what's the issue here? Well, there are a number of reasons why this is challenging here. So one is that to optimize something, you need an objective function to optimize, and for stochastic models, it's not always very obvious what your objective function should be. If you're kind of a statistician, you know that the correct thing to optimize in some kind of formal sense is the likelihood function. But here for these models, we often don't know what the likelihood function is. So, I mean, that's kind of a good ideal, but it's not necessarily trivial. And as I've said, just plain optimizing anything, even if you optimize the right thing, that is the likelihood, right? That's the so-called maximum likelihood approach. Again, in these kinds of settings where you've got very poor data, but very complex models, it really doesn't make sense to just kind of pick an optimum, okay? So this idea of focusing on a point estimate for your parameter values really doesn't make any sense at all. Okay, so that's where the Bayesian approach really comes in, because it accepts uncertainty in what you know. So these Markov chain Monte Carlo algorithms then allow you to explore the posterior distribution that is associated with your model parameters. Okay, So we can explore the parameter space. We kind of get more samples where we're more likely, where our parameter values are more likely to be. Yeah, and so by looking at the posterior distribution, where it peaks, we know that the parameters are likely to be. But we can also look at the range, the spread of the distribution to see how uncertain we are. We can look at correlations between parameters to understand confounding, identifiability problems, etc. So these Monte Carlo algorithms are really very powerful. Of course, they're computationally intensive, but it's not clear that there's an alternative to a very computationally intensive solution for these kinds of complex problems. So, you may as well kind of do it properly and do the Bayesian analysis. Now, of course, Bayesian inference is a massive field, and not all of it is directly relevant to this problem, but in the context of this kind of program and the kinds of problems I'm talking about here, I guess there are three different classes of, also not all Bayesian analysis is Monte Carlo based. I mean, that's worth saying as well, but here I'm focusing on Monte Carlo algorithms. So there are three kind of broad classes of Monte Carlo algorithms that I'd say are kind of obviously relevant to the kinds of problems that exist in this field. So there are ABC algorithms, okay, and everything I say here is a kind of simplification and a generalization. So I call ABC algorithms global, I call MCMC algorithms local, but there are local ABC algorithms and there are global MCMC algorithms, right? These are generalizations, but typically you think of ABC algorithms as being global searches of the parameter space, okay? They are likelihood free, and by that I mean you don't have to be able to calculate probability distributions associated with your Markov process. You only have to be able to simulate it. But they're approximate, as the name suggests, right? The A in ABC is for approximate. Okay? The algorithms that I really liked and I talked about more at the opening workshop are these particle MCMC algorithms. There's also a variant of those that are likelihood free. Okay, so particle MCMC algorithms are not necessarily likelihood free, but the simplest variant of them is. Okay, and so again, all you need to be able to do is to be able to forward simulate your model. So that's good. And because they can exploit the Markov property of your process, they are sort of more efficient. And because of the way they're set up, that I'll explain very briefly, they can also be exact. So this is kind of remarkable that despite the fact that you can't evaluate the likelihood of your process, you can nevertheless construct an MCMC algorithm that targets the exact posterior distribution, which clearly implicitly involves that likelihood that you don't know. Okay, so these are kind of magic algorithms, but it's not magic, of course. It all works. And of course, you can actually go beyond these likelihood-free algorithms. If you're prepared to evaluate likelihoods of sample paths, you can develop much more efficient algorithms. So I'm not going to talk about these at all today, but again, at the opening workshop, I did talk a bit about how you could take these particle MCMC algorithms and turn them into likelihood-based algorithms to make them more efficient. Okay? So again, if you're interested, you can go back and watch that talk. But I should emphasize that you only have to be able to evaluate likelihoods of sample paths, right? You don't have to be able to evaluate the transition kernel of your process. So obviously, if you had to evaluate the discrete time transition kernel, that would make them of limited use, okay? But often you can evaluate likelihoods of sample paths even if you can't kind of solve the master equation. So this is not as restrictive as you might think. Okay, so this issue of modularity and decoupling is just as important for inference as well. You know, you just want to model, you want to do inference, right? You don't want to think, okay, I've got this model, I now need to spend 3 months writing an inference algorithm for it, right? You want to have a generic inference algorithm and you want to have your model representation decoupled from that, so when you've got a new model and a new data set, you can just plug them in and go, okay? That you want to do as well. And of course, the nice thing about these likelihood-free algorithms is you get that for free, okay? So that's why they're so popular, essentially, is they completely decouple the whole simulation of the process from the inference algorithm, right? So you write your inference algorithms in such a way that all you have to do is drop in a forward simulator of the process and away you go, okay? So that's very, very attractive. It has lots of advantages. It has some disadvantages as well, but it has lots of advantages. And in particular, decoupling from the simulation algorithm also has the advantage that, you know, you can start off using an SSA, and if it's not fast enough, you can drop in a hybrid simulator instead, okay? So actually decoupling from the simulation methodology actually has additional advantages over and above decoupling from the model representation. Okay, so that's why these algorithms are so popular in so many areas. Okay, you pay a penalty in terms of computational efficiency, but that's usually a price worth paying. And so I should just say that if you're using one of these likelihood-based MCMC algorithms, there is no reason why they can't be decoupled from the model representation, right? They actually can't be decoupled from the simulation methodology, right? They have to have their own kind of simulation schemes embedded in them, okay? So that's a potential disadvantage. But they could be decoupled from the model, right? There's no reason why you can't have, just feed a model into a likelihood-based algorithm as well. It's just, it requires kind of programming skills that many statisticians don't possess to do that. So again, this is why people really like these likelihood-free algorithms. Okay, so I should say what I mean by a partially observed Markov process. So I mean, we've got a Markov process we will call capital X. We're going to assume we've got some observations on it, but probably those observations are going to be in discrete time, even if our process evolves in continuous time. So just for simplicity, we could imagine integer time observations, though you'll note in my example they're not integer time. We can often calculate these sample path likelihoods, okay, but in fact, nearly always we can't calculate the discrete time transition kernel, right? That requires solving the master equation or whatever. It's usually intractable. But it doesn't matter as long as we can simulate from it, okay? So we can simulate xt given xt minus 1 even if we can't evaluate its probability distribution. And we're going to assume some kind of observation process. And again, this can be a very partial observation. So there is a state of your system at time t, but all we're assuming is we have some probability model for our observations. So we might only be observing some of the species, we might be observing them subject to noise. We could even, in principle, be observing some weird function of the species. So for example, in this particular example, it might make sense to observe, twice the dimers plus the monomers, right? Because that's actually the thing you could easily construct a fluorescent reporter system for, right? So this could even be some function of the state of the system, okay? But as long as there's a probability model for it, it doesn't matter. For the exact methods, we need to be able to evaluate this probability model. And usually that's not a problem, right? The problem is usually evaluating this thing. Evaluating the probability model is usually not a problem. But again, for the ABC methods, you don't even have to be able to evaluate the measurement model. As long as you can simulate it, you're good to go. Okay, so the Bayesian inference problem then, in this context, is what we call Bayesian inference for a latent process model. So here the latent process is the Markov process, or the other kind of, whatever your stochastic biological process is that you don't perfectly observe, that's going to be X. It's going to depend on some parameters theta. They might be rate constants. They might be any of the other parameters we've been talking about. We're going to have a model for the process, given those parameters, that we can at least simulate. We're going to have some data. And the data model might depend on parameters, right? So you might have unknown parameters in the observation model, right? You might know that you've got noisy observations, but not know how noisy they are. And you might want to infer that parameter as well. That's fine. So we can write down the joint model. And Bayes' theorem just says, well, the posterior distribution is proportional to the joint distribution, right? That's it, okay? The normalizing constant is going to be a bit tricky, but often you can get away without evaluating it. Okay, and if you're using some Monte Carlo method, okay, you can think about the joint posterior distribution for theta and x, and then you can just drop your x samples to get the marginal posterior for theta given y. Or in fact, many of these methods, because they're simulation-based, you can just ditch the x completely if you're really only interested in the parameter inference problem. But note that sometimes you are genuinely interested in the unobserved state, right? You want to make inferences for that as well as the model parameters. Okay, so there are loads of practical issues that nobody ever talks about in talks and people hardly ever talk about in papers either, to actually getting this stuff to work. So it all sounds very easy, but in practice there are lots of complications that make it just a little bit fiddly and messy in practice. So the first thing is that your prior distributions are really important, okay? It's, what you would ideally think was that, okay, I can just put down any prior I like without thinking about it, because I'm going to let the data speak, right? This is the kind of old cliche. I want the data to speak. Well, the data isn't going to speak. As we said, in most cases, your data is not going to tell you very much about some of the parameters. So thinking about your prior distributions is really important, okay? So in particular, if you just bung down some vague prior, okay, that's going to cover a huge part of parameter space. And probably you've not thought about how the dynamics of your model vary as you do crazy things to the parameters, okay? So some models will have, in the regime that you've got in your head, they behave perfectly nicely. But with some parameter combination, actually, some of the species just explode, okay? So the SSA never finishes and things like that, right? So even if in your head, right, your model should simulate quickly, if you bung down a crazy, vague prior distribution, you're probably going to be covering parameter regimes where your model is doing all kinds of weird, non-physical things that are going to take a long time to simulate, and they're just generally going to be bad, okay? So you should think about your prior, use that to kind of constrain the space of parameters that you're exploring, right? You do that with optimization methods, right? With optimization methods, you don't just say optimize, right? You put bounds on parameters, you think about the space you're interested in an optimum, right? There are regions where you don't care if there's an optimum because you know that's crazy, okay? So you use the prior distribution to constrain your space. So personally, and also different priors make sense on different scales. So for example, with these rate constants, right, they've got to be non-negative, of course, but the way they behave, it's sort of more natural to think about your uncertainty on the log scale with these parameters. So I often like to use just finite uniform priors on the log rate constant, right? So I think at a lower bound, I really don't want to think about rate constant smaller than that. I really don't want to think about a rate constant bigger than that. Between, I don't really know, so a uniform on the log rate constant scale kind of makes sense in many cases. The other thing is, if you just got loads of parameters, this causes lots of problems. So in this model, for example, there's the dimerization and dissociation rate constants, where the data will probably identify their ratio quite well, but not the individual values, because you're observing over quite long time scales, where it's kind of hard to distinguish, you know, making the dissociation constant and the binding constant a bit bigger from making them a bit smaller, okay? So you get this strong posterior correlation. But what that means, again, is that your model will explore very high combinations of those two rate constants, and the same with the binding and unbinding rates on the DNA, right? If you don't stop your model from exploring those kind of weird combinations, then it will explore them because the data is not telling you not to, okay? So again, if you've got some unimportant parameters or some parameters you've got a good idea about, just fixing some of those to plausible values can just make your computational effort a lot easier. And I'm going to do this here, actually. I'm going to just do inference for 4 of the rate constants, just to make things simpler. It's not that the methods don't work for all 8, it's just a bit simpler, and everything runs a lot faster if you're not trying to do too many parameters at once. Okay, so this is my one-slide summary of PMCMC. If you want to know more, yeah, go back to my other talk. So what is it? It's a Markov chain Monte Carlo algorithm using a random walk proposal to explore parameter space. So you started off somewhere in parameter space, you let it wander around. The way Metropolis-Hastings algorithms work is you bias the acceptance probability of each proposal in order to make sure that the equilibrium distribution of that chain is the posterior distribution that you're interested in. Now, it turns out that for these models, to evaluate that acceptance ratio, you need to know the likelihood of the model, and for these models, you don't know the likelihood of the model. So the particle MCMC trick is then at each iteration, you run a particle filter, which gives you an estimate of that constant that you don't know that you need to know to run an MCMC algorithm. And the magic is that despite the fact that particle filters are approximate and that you only get an approximate estimate of that quantity, nevertheless, the target distribution of this MCMC algorithm is the exact posterior distribution. There is no error in the target distribution at all. And that seems magic when you first hear about it, but it's not, it's true. And these algorithms, they can either target directly theta given y, which is all I'm going to do here, or if you're interested in the state, they can target theta and x given y. And again, in both cases, it is the exact target. There's no approximation introduced by any of the kind of steps in this algorithm. The equilibrium distribution of the chain is the exact posterior. Okay, and again, at the opening workshop, what I talked about is how to make these more efficient if you're prepared to use likelihood-based methods. Okay. Right, so that's PMCMC in a nutshell. So we can run that for this problem on the 4 rate constants. So what I did was I didn't bother with the DNA binding and unbinding constants because the data isn't going to tell us anything about those. And I actually solved this strong confounding between the binding and dissociation of the dimers by fixing the binding constant. So I'm only doing inference for the dissociation constant. So that makes things a lot easier, obviously. And this is the kind of thing you get. You get these trace plots. You can look at the autocorrelations. What you really want to see is those autocorrelations dying away to 0 very quickly, which they're clearly not doing here. And these are your marginal uncertainties for each of these rate constants. So this is the translation rate constant, this is the dissociation constant, this is RNA degradation, this is protein degradation. So our information is summarized in this sample, and we can look at this sample, we can slice and dice it in any way we like. Like I said, I put uniform priors on the log constant, so it makes sense to look at the log transformation. So you just log transform all your samples and look at those instead. Okay, and so these were uniform priors. So any deviation from uniform here is kind of information in the data. So we've learned a bit about the translation constant. We've learned an awful lot about this dissociation constant. This is really pinned down very accurately. We've learned a bit about these. It all looks like it's working fine. We can also look at correlations between parameters. So here, for example, you look at this and you see that there's quite a positive correlation here and here. Okay, so what's that? That's a positive correlation between the RNA degradation rate and the translation rate. So what that's saying is that on the basis of the data, okay, it's hard to distinguish a particular kind of pair of constants and the way the model would behave if you made them both a bit bigger. Yeah, there's this kind of partial confounding. So again, by looking at relationships between variables, looking at correlations in the pairwise plots, we can sort of untangle what the data's telling us, what the model's really what the data's really identifying, what it's not identifying, etc. But anyway, we've learned quite a lot here. We've got nice distributions. This all looks to be working reasonably well. The run is nowhere near long enough, right? I ran it for like 2 days, and I should have run it for like 2 weeks. But it's all working. Okay, but there are a lot of parameters here. So the nice thing about these PMCMC algorithms is you know the target is right no matter what. But in practice, the way that chain mixes and how fast it mixes and how well the scheme works, how efficient it is, depends a lot on various tuning constants. So you've got to tune your proposal process, you've got to tune the number of particles you use in your particle filter. You've got to initialize the sampler quite well, because if you initialize it out in the tails of the distribution, it kind of sticks there and finds it very difficult to find the region where the probability mass is. And of course, if you kind of knew what the posterior distribution looked like, you wouldn't be doing this in the first place, right? So initializing is a little bit sensitive. So, there are issues with doing this, but at least you know that the target is right. So this is still my kind of fallback method. Okay, but there are other alternatives, okay? So ABC has been mentioned a few times this week. So what's ABC? Well, ABC is a really simple idea. You've got your joint model, okay, for your parameters, your observation, and your data. So it's dead easy to simulate realizations from that model. So essentially, we can pick a parameter and we can simulate a data set. So having picked a parameter and simulated a data set, in some sense you want to compare the simulated data set with a real data set. And it's pretty obvious, if you know anything about rejection sampling whatsoever, that if you just look at your simulated data, see whether it matches. If it matches, keep it. If it doesn't, try again. It's obvious that actually that's going to give you exact realizations from the posterior distribution, the theta given y. Okay? So that's kind of easy, except of course it's not easy, because the chances of your data matching is going to be negligibly small, and in fact if you've got any continuous data values, it's going to be 0. Okay, so this isn't going to work in practice, but this is the idea behind ABC. And so the relaxation of it is to say, okay, I'm not going to require that my data matches perfectly. I'm going to define some metric on the data space, the sample space, and I'm going to accept my value as long as this metric is below some threshold. Okay, so that's the ABC idea. And obviously, well, maybe it's obvious, maybe it's not, but it's nevertheless true that as you make epsilon smaller, this distribution, this ABC posterior, gets closer and closer to the true posterior. But notice that for no finite value of epsilon is it the true posterior, right? So this is an approximate method, okay? It's not like those MCMC methods. This is always an approximate method. And if you think about it, it's kind of obvious that it's nearly always going to be over-dispersed relative to the true posterior, right? You're going to let things in that you shouldn't, right? So that's going to naturally cause it to be a bit over-dispersed, okay? Now, there are still lots of problems with this, but this is the basic ABC idea. So if we just use simple Euclidean distance as our metric, we can run this, we can get parameters, and what we find is that these are kind of rubbish distributions, okay? They're very, very over-dispersed relative to the true posterior. And when we look at this, we see that they're more or less uniform, okay? So we've really not discarded many, right? They're almost kind of square distributions. We've really not learned very much here at all. The one thing we have learned about is this kind of confounding here, and actually we've overestimated that. So this hasn't worked very well at all. So why hasn't this worked very well? Well, this metric is really important, and just using Euclidean distance on the sample space is crazy. Okay, if you're doing inference for the mean and variance of a normal distribution, right, you wouldn't simulate loads of values from a normal distribution and check to see if every data point matched every data point, right? What would you do? You'd look at the mean of your data and the mean of the data you're trying to match, and you'd use that, and you'd use the variance, right? So you'd introduce some summary statistics that describe the distribution that weren't so sensitive to noise, and you'd match on those, okay? So that's what people do in ABC as well, okay? So statistically, we know what the correct thing to do is. Statistically, we know the optimal thing to do is we take the sufficient statistics of the likelihood model and we use those to define our metric. Now, of course, the problem is that for these models, when we're doing ABC, we usually don't know the likelihood model, we usually don't know the sufficient statistics, and in fact, for most of the models you would do this on, in fact, sufficient statistics won't even exist, okay? So we can't do that, but that's the intuitive idea. We want to pick some summary statistics that are sort of like sufficient statistics, so things that really summarize the behavior of the process, and then we're going to define a metric on those, okay? So what might we do for time series? So the obvious kind of thing to do for time series, how do you summarize a time series? Well, you might look at the mean of the values, you might look at the variance. You know the correlations are important, so we maybe look at the lag1 and lag2 autocorrelations. If you've got multivariate time series, you look at the cross correlations between them. Okay, and by the time you've done the mean, the variance, the lag1 and lag2 autocorrelations and cross correlations, you've captured a lot of structure in multivariate time series data. So that would be a good start. And so there, for this problem, you've immediately reduced kind of the thing you're aiming to hit from being 100-dimensional to 9-dimensional. So that's a good thing to start with. But it's actually even better than that suggests, because the things you're trying to hit now are rather insensitive to the noise in the simulation process. So it's actually, you know, it's much better than a kind of 100 to 9 ratio there, because, you know, this was 100 crazy things to try and hit, and these are 9 sensible things to try and hit. Okay, so that's basically how you do it. But then you still got to define a metric on these summary statistics, and there are lots of sophisticated ways to do this in the literature that are you know, in some sense optimal. Here I've just done something really simple, which is just standardize them so they all have, you know, variance 1, so that at least we're measuring them on different scales. You know, otherwise, you know, the mean would swamp the autocorrelation, because the mean is like 100 and the autocorrelation is 0.1, right? So it wouldn't make sense to define a Euclidean metric on that, okay?
That's a quick question.
Yep.
So I'm a little confused by one thing. So you can summarize the mean, the variance, all these things.
Yep.
And then you simulate one path.
Yep.
How do you match the... I don't understand what you mean by matching the variance here.
Oh, sorry, I mean the sample variance of the trajectory.
Ah, okay.
Yeah. So these are all just statistics of the data.
I understand.
Yep. Okay, cool. Right, so there are still issues here that I'm glossing over, but, you know, that's the basic idea. And so when we do that, things suddenly start working much better. We can basically bring our epsilon threshold down quite rapidly, and we get much better posterior distributions. They're still very over-dispersed relative to that MCMC scheme, but things are basically working much better, and we're getting, you know, much more sensible, you know, looking posterior distributions. So that improves things a lot. So that solves one of the problems. So that solves the issue to do with the dimension of the data. That's what summary statistics are all about. But there's still a bit of a problem if you've got a high-dimensional parameter space. So here we've only got 4 parameters, so it's not the end of the world. But if the parameter space is large, clearly just picking from your prior and hoping that that's going to be a good thing is going to be a bit problematic, okay? Because probably the posterior is going to be concentrated on a really tiny volume inside, you know, the kind of support of the prior. So that's kind of not so good either when you've got lots of parameters. So again, it was mentioned, I think Kevin mentioned, that you can kind of just gradually zoom in. So you can start picking from the prior, discard things that are completely crazy, and then gradually zoom in on promising parts of the parameter space. So that's the ABC SMC idea. That I'm kind of running out of time, but I'll just explain very quickly. So the idea here is, from an ABC perspective, we're just going to gradually reduce the tolerance threshold, okay? So we're going to start off simulating from our prior, so that's epsilon equals infinity, and we're going to gradually bring it down as close to 0 as we can, okay? And do this in a sensible way. But the question is, what's a sensible way to do this? We can't just blindly resample at each stage, because that would be like pretending that our prior had changed at each stage, and then it won't converge to anything sensible. So we've got to do this in the right way. And the right way is kind of given to us by the theory of sequential Monte Carlo samplers, which are a general theory that work for any kind of sequence of distributions. So basically, it's the same idea, though. You've got a sequence of distributions where the first one is easy to sample from, the last one is the thing you're interested in, and they kind of bridge gradually. How can you sequentially transform a set of samples from the first distribution to the last distribution? Well, the theory of sequential Monte Carlo samplers tells you how to do that. It's just kind of important sampling ideas. So here's how it works for ABC SMC. You have a set of parameters at one scale. You then pick from that weighted set of particles, so you now have weights associated with the particles that you use for resampling. So you pick from that weighted set of particles. You can propagate through a perturbation kernel, so you don't get so much problems with degeneracy. You might just perturb them a bit, just like you would in an MCMC algorithm. You then simulate from your model, and then if your simulated data is too far away, you reject it. Otherwise, you go back and start again. However, when you find one that you accept, you actually don't just accept it as an equally weighted sample. There's a weight you have to calculate to correct for this fact that you're doing things sequentially and you're resampling from one distribution to get the next. And again, it's the whole likelihood-free trick that there's things relating to the target on the top, there's things relating to the proposal on the bottom, but the nasty likelihood that you really don't want to evaluate occurs on the top and the bottom and therefore cancels out. And so we're just left with easy things in this weight calculation, okay? And so these weights just correct for the fact that we're kind of doing this sequential procedure, and you know, if we wanted to converge to something sensible, we need to do something a little bit sensible. Okay, so that's it, basically in a nutshell. And this works as well. So the idea is you run a bunch of iterations, not too many. It's not like MCMC where you run it for millions of iterations, but at least a handful of iterations. So at iteration 1, it kind of looks a bit rubbish. You've just got rid of the dross. Okay, iteration 2, it's starting to look a bit more sensible. If I fast forward to iteration 10, it's now looking pretty good. In fact, it's looking at least as good as that, one I showed you previously. And that one I showed you previously was done with like zillions of samples. So it's done pretty well to get there that quickly. Okay, and then on the log scale, again, you start off at uniform. At iteration 1, you're just chopping off the dross, but you're still kind of covering a lot of space. But you gradually zoom in, okay, and it gets better and better at each iteration. I think it's easiest to see on this one. Okay, so this is iteration 1. Remember, we start at uniform, and the idea is that we want to gradually zoom in on the posterior. So this is iteration 1, iteration 2, iteration 3. You can see we're gradually zooming in, iteration 10, gradually zooming in on the posterior. I mean, there are various artifacts in here that I can talk about if you're interested in, but that's the basic idea of how it works, okay? And in high-dimensional parameter spaces, that's a good thing to do. Okay, so what are the pros and cons of all these methods then? So all of these likelihood-free methods are pretty computation intensive and pretty inefficient in some sense. But if that's your technology, that's your technology. ABC is very, very general. So for example, you don't need to apply this to Markov processes. If you've got a non-Markov process, it's fine. You can use it on non-Markov processes. It can be applied to essentially any setting you like. They also parallelize extremely well. You can even parallelize across a cluster very, very easily. Really parallelizes nicely. So that's very nice. Yeah, people like it just because it's intuitive. It does have this problem, though, that it is approximate and it's over-dispersed relative to the true posterior. And your tuning parameters really matter in the sense that they really affect the final distribution you end up with, and that's always a bit of a worry, particularly when you're kind of working blind. You know, here you can tune it to match a PMCMC posterior, but you know, if you're doing this in real for real life and you don't know what the answer is, right, it's kind of hard to tune it and know whether you're really doing well or not. The particle MCMC algorithms I really like because I know it's targeting the exact posterior. So now, there is this issue for all of these Markov chain Monte Carlo algorithms that actually in practice for a finite length run they tend to kind of be under dispersed relative to the true posterior. It parallelizes okay actually over multiple cores on one machine. It doesn't parallelize so well over a cluster because of the granularity issues. But it works. So for me, it's very much like the SSA for forward simulation, right? There are all these fancy methods, fancy analysis methods, fancy simulation methods, but when you really care about the answer, you always just kind of fall back on the SSA, right? Because you know that's going to work. And for me, these particle MCMC algorithms are like that. There are all kinds of other clever, fancy things I could do, but if I really care about the posterior, I just find a big computer, I stick my PMCMC algorithm and I just let it run for a couple of weeks because I know that that's going to do something sensible, right? So it's very much the same kind of thing. Okay, but of course you can put these two things together. So one thing that I find useful is to do an ABC SMC first of all to get a kind of ballpark idea of the posterior. And then I can use that kind of rough guess at the posterior to tune the PMCMC algorithm, right? So all those funny constants in the PMCMC algorithm, we can tune on the basis of a rough and ready guess at the posterior. And also, if we've got a rough and ready guess at the posterior, we can run a bunch of parallel PMCMC chains initialized at a sample from that ABC SMC posterior. And that will get around the problem of having to kind of burn in these MCMC chains for every different chain. So that's kind of a useful thing to do as well. Okay, so to wrap up, Bayesian inference for complex simulation models, these likelihood-free methods are very attractive. There are lots of likelihood-free algorithms, not just one. Some of them are exact, okay, and that's worth knowing about, right? It's not obvious that you can do exact inference for models where you can't compute the likelihood, but you can, okay? PMCMC is great, but there are lots of other algorithms. If you're determinedly non-Bayesian, there's even a maximum likelihood version of this called iterated filtering. And I think it's worth thinking about, you know, hybrid procedures as well. But I've run out of time, so I'll just leave you with a few references. Thanks very much.
Few quick questions.
Can you comment on these kind of ideas to pick the summary statistics a bit more kind of cleverly?
Yeah, so as you can imagine, there is a massive literature on this. But a lot of the literature kind of focuses on, I've come up with a nice, really good set of summary statistics. How can I pick which are the best ones? How can I weight them into a metric, etc., right? There's no real magic for, you know, constructing good statistics kind of completely ab initio. Yeah, there's very little theory on that. But once you've got a candidate set of sufficient statistics, then there's all kinds of theory for how to do something sensible with them. But for really coming up with these are the best sufficient statistics for this problem, there's not as much as you'd hope.
So you work with the log transforms of the rate constants.
Mm-hmm.
But in the beginning of the talk, you mentioned that one can check whether a reaction exists or
Yeah.
just based on the values of the rate constants.
Yes.
Near zero or not. So,
Yep.
So when you put them under a log transformation, doesn't that cause a problem if you have rate constants nearly zero?
No. So you can have a binary indicator that says is it 0 or not, and then conditional on it not being 0, you could then have this uniform prior on the log rate. That would be fine.
Okay.
There are lots of other things you could do, but that's something you could do.
Okay, so let's thank the speaker again. And